Hey folks, Mrs. White here. Hope your homework last night went well. We're going to keep moving forward. Today we're going to look at section 5.4, which is the first time we're doing graphing in this section, and it's going to be graphing specifically square root functions. So we're going to review a little bit about square roots, where they come from, and how we can go about graphing these pretty efficiently. There's a couple strategies that if you Googled it, you would see online. Some of them involve translations. What we're going to focus on today is how can we create a table of three values, which I know you don't love creating tables, but it's actually a little bit easier to go through that process versus remembering a bunch of translations. So today we're going to start by talking about the homework that was due yesterday, which is kind of looking at are these two things inverses and how we can use composition of functions to determine that. So I have a key for you right here we'll discuss. Then we're going to hop right into the section 5.4, where do square roots come from? It's actually kind of related to inverses. What does their parent function look like? And then how can I graph them fluidly? We'll do 3 together. And then you're going to have 6 graphs for homework. On the Google Classroom, there is this worksheet attached. This worksheet includes the 3 that we're doing together on the front, and then on the back is the 6 for homework. So if you have access to a printer, I'd probably pause the video right now, print this sheet right out, because it can kind of work like a note-taking guide for you when we do the first 3 examples. Okay? So let's hop right into talking about our homework from last class. So as you probably have noticed over the last couple weeks, homeworks now, instead of being, if you've had me traditionally, they're out of 4 points, they're now out of 10 points. Starting with this assignment and the following assignments, they are going to be somewhat graded on correctness, and they're going to be out of those 10 points. So in this instance, I'm probably going to make each of these worth, a handful of points, and based on the work that you've done and or errors that you've made, we'll either add points or take points away from that. So let's just talk about how can we determine if two functions are inverses, okay? And we're going to specifically not find the inverses, okay, but I want you using composition of functions to do that. So what we learned in our last class is that two things are going to be inverse functions if, when you plug one into the other, you end up with the identity function, which is y equals x, okay? And I didn't put the y equals x here, but I just solved it to just be x. If that's the case, then that's a good sign. So I started off by doing f of g of x. So we have an f and a g. F of g of x means I take my g of x, plug it into the f function. So I took my g of x and plugged it in right here, okay? And then I just simplified. So the 7 and the negative 7 cancel. I end up with just x. That is my identity function. That means so far these two could be inverse functions. However, if you get a yes, you have to keep going and check the other composition because we know they're not always the same. So now we're going to do the opposite. Instead of doing f of g of x, we're going to do g of f of x. So I'm going to start by taking my f of x function, which is x minus 7, and I'm going to plug it into my g1. I'm going to plug it in right here. So again, the minus 7 and the plus 7 canceled. I ended up with just x. That is my identity function. Boom, I got a yes again. If you get yeses on both, then you'd say they are inverses of each other. Okay? Next couple ones are no's. Now, once you check one composition and it's not going to cancel out perfectly to just be an x, then you do not have to do the second one, okay? But I included both just in case if you checked this one first or if you checked this one first, you can kind of take a look at both of the processes for each. So first thing I did was f of g of x. So I took my g of x and I plugged it in for this x right here into my f of x function. So instead of 1/2 x, I had 1/2 times 2x minus 4/3 plus 3/4 on the outside. Now, we've seen a little bit about inverses, so you might think, okay, those look like they're going to cancel, and these are inverses, so they look like they might cancel. So at first, this feels like it could work. However, if I plug those in and start simplifying, I distribute a 1/2 across here and here. You go across the top, across the bottom. That simplifies to be 1x, which is nice. Then here, we'd also go across the top. 1 times 4 is 4. And across the bottom here, 2 times 3 is 6. Well, 6 is the same thing as a negative, right? Because the negative here, negative 2/3. And I don't even need to add those together because I know negative 2/3 and positive 3/4 are not going to cancel out. Okay, leaving only the x. This felt good at first, right? But because these will not cancel, the answer is no. In order for it to be an inverse, they have to both be yeses. So the second you get a no, you don't actually have to do the second composition to check it. Once you get a no, you're done. Okay, so if you stopped here, and you just have one box filled out, perfect. Okay, if it's a no, that's fine. If you did the opposite composition, you would have plugged in f of x into your g function. So I would have taken this and plugged it in here, okay? So I have 2, but instead of x, again, I plugged in the other function, 1/2 x plus 3/4. I'm going to distribute again. That's simplified to be 1x, which was lovely. And then I sent the 2 to the 3, which was 6, and then the 1 to the 4, which was 4. So positive 6/4, which simplified to be positive 3/2. Well, is 3 over 2 and negative 4 over 3 going to cancel? No, they're not equivalent. They're not going to cancel. This one's also a no, okay? Let's go to our last one here. I'm going to, again, do my compositions. I'm going to take my g of x. Okay, I'm kind of working backwards. I'm going to plug it into my f function. So I'm going to take this and plug it in here. And I know this is a little hard to see just in the way that it's scanned in from my computer, but this is a power of 3. You can see it here. So I have 2 and then x to the 3rd, but instead of x, I'm putting that in and raising that only to the 3rd. 2x is not being cubed. If it was, it would have parentheses around both of it. So anyways, I'm going to send the cube here. So I have 1/3 times 1/3 times 1/3. Across the top is 1. Across the bottom, 3 times 3 times 3 is 27. Then I have the square root of x, right? Because my number here, okay, my index number is going to be, if it's invisible, it's 2, okay? If there's a 3 here or a 4 here, it would be a 4th root. And we'll see that a little bit more in the next section. These aren't going to cancel, okay? A square root raised to a 3rd power are not inverses. Now, if it was a square root raised to the 2nd power, squaring a square root, we know from our quadratics unit, cancels, okay? And then we'd have just x. Now, I know right now that the fact that the square root and the cubic aren't the exact inverse of each other, they're not going to cancel out. That means this is never going to be just an x by itself. It's always going to be the square root with the cube, so I can just say no right away. You don't actually have to simplify it all the way down because I can identify right now that it's not going to. So you could stop here with your no. You don't have to do the second one, but I showed it just so that you folks could see it if you did the opposite. So here I'm going to take f of x and plug it into my g function. So I'm going to take this and plug it in underneath that square root sign. So I have 1/3 times the square root of, instead of x, I put in 2x to the 3rd. Now, one of the properties that you may or may not have seen before, I know we talked about it in my class, was that you can distribute this root to everything underneath if it's a monomial. So this is a mono. It's everything all squished together, so I can make it a square root of 2, and I can make it the square root of x to the 3rd. So once I kind of distribute that root to both of the pieces of my monomial, I can identify, oh yeah, square root of x to the 3rd is not going to cancel nicely, okay? This would have to be the exact same power as my index, and my index here is technically a 2. So since these won't cancel, I know it won't work. You also could identify here that these aren't going to cancel, right? This is a constant, this is a constant, this is 1/3, this is square root of 2. They're not the same thing, okay? So if those were going to cancel out when you multiply them to be 1, then it'd be good to go, but they're not either, so it's automatically a no, because that won't become 1. You will have an opportunity to practice inverses a little bit more. We'll see it as our sit and begin in our next lesson. So writing them and being able to do compositions with them is going to be important. Okay? But today we're moving on to something a little bit different. We're looking at some graphs. So before we talk too much about our square root graph, I want to talk about where does it come from. So we're going to find the inverse of x squared. Okay? Then we're going to graph our x squared. And then we're going to graph the inverse also on this same coordinate plane over here. So let's start off just reviewing how do we find the inverses. Okay, remember this little notation means inverse. It also says find the inverse. So to do that, I'm going to assume this is my y, and I'm going to flip-flop my x and my y's position. So instead of y equals x squared, I'm going to have x equals y squared. Now I need to get my y alone in positive. So just like we spoke about in our sit and begin and have talked about in the past, the way to cancel out a square is with a square root. So I square root both sides, cancel, cancel, and I'm left with my inverse. So my inverse of f of x is going to equal the square root of x, right? This is just y, so I can plug it in with my f of x piece. This is my parent function of my square root, okay? And I could make a little table for that if I wanted to. We'll just do a quick one, really nice, easy. We'll do 0, 1, and then 4. And I'll explain to you why I chose those later. The square root of 0 is 0. The square root of 1, if I plug this 1 in here, is going to be 1. And then the square root of 4 is going to be 2. So I'm going to go for my inverse over 0, 0, over 1, 1, over 4, up 2. So here is my square root function. In fact, that's going to be the parent function, the most basic of them all. Now, if we look at our original function, okay, they want us graphing y equals x squared, so it's going to be a quadratic. So it's going to be a parabola. It starts here, and then goes here, and then kind of curls up this way. Okay, that's the parent function for our quadratics. It does say only do where x is greater than 0. So all of this half of my polynomial, not polynomial, well, it is a polynomial, but all this half of my quadratic I'm not going to include. I just want to include where x is 0 and greater, which is going to be this side. Now, if you take a look at that, folks, hopefully you're noticing, oh yeah, these are inverses because they're reflected right over that line, y equals x, right? Our identity function. And that's where this graph is going to be coming from. Okay, our square root graph is going to be always the half of the parabola, that would be the inverse of it. Okay, so it's always going to look like just half that curve. Let's look at another one that's a little bit more complicated so we can show that they are actually a reflection over the line x equals y. Let's start off by writing our inverse of this function. So this is my y, that's my x. I'm going to flip-flop their locations. So I'll have x equals y squared plus 1. To get my y alone in positive, because this is not part of the squared, I'm going to minus it. Then last step, to get rid of the squared on my y, I'm going to square root it, and then I have to square root both of these. Now these are a binomial, right? 2 pieces. So I can't just distribute that root to both parts. I have to leave both chunks underneath my square root sign. Now my y is alone and positive. I can write it as a inverse in function notation. So the inverse is the square root of x minus 1. Okay. Now we'll give this a graph. I'd start by making a table. I'm going to start out with 1. I'm going to start out with the number 2, and then I'm going to actually go to the number 5. And I can do these mentally. When we learn how to graph these in just a couple minutes, you'll see why I chose those values. So if I plug in 1 here, 1 minus 1 is 0. The square root of 0 is 0. 2, if I put a 2 here, 2 minus 1 is 1. Square root of 1 is 1. Lastly, I'm going to plug in 5. 5 minus 1 is 4. Square root of 4 is 2. So I'll graph this up. I'm going to go over 1, up 0, over 2, up 1, and then over 5. So 1, 2, 3, 4, 5, up 2. And here's that little curve for the square roots. Then I'll go back to my original function right here. This is going to be a quadratic. Again, that's going to be shifted up 1. So instead of starting at 0, 0 like this one did, it's going to be shifted up 1. And then it's going to go here in this direction like this. Again, I'm not including anything to the left of 0, right? I want my x values to be 0 or greater. So boom, look at that. You can see that clearly that is a reflection over the line y equals x. Okay, so this is where our square root graphs are coming from. If you think about it, we spend a lot of time graphing quadratics, right? We spend a lot of time making these U-graphs. Well, now we're going to spend some time learning their inverses and graphing that. And the way we're going to do it is by creating this table each and every time, okay? Even for ones that are going to be a lot more complicated than this or our original parent function. So let's take a closer look at the parent function. So if you were to start your official notes right now on how do we go about graphing square roots, this is where I would definitely be starting. So if you haven't already kind of given it a go and pulled out your notebook, now would be a good time. We already talked about a little bit what this graph looks like, but let's make an official table including positives and negatives to see why that shape actually comes along, aside from the fact that it's the inverse of a quadratic. Okay, so usually I know how you folks are. You probably pick like some negatives and positives. You try to probably avoid the negatives, but we're going to include them. So let's maybe do like -2, -1, 0, 1, 2, 3, 4. And then I'm going to choose some ones that I know are going to work better, like 9. Let's just throw a 9 on in there. So to create an XY chart, we pick our x's, then we plug them in and get out the y. So I'm going to take this -2 and I'm going to plug it in right here. And I end up with the square root of -2. Now, hopefully right now you're like, square root of -2, I need a calculator. Maybe that's what you're thinking because you can't do it in your head. So you grab a calculator, you plug in square root, you plug in the negative sign, not the minus sign, and 2, and then you press enter and you're going to get error. Why is this going to result in an error? Because any negative under a square root sign is imaginary. This is technically equal to I root 2, okay? And I root 2 is not graphable on this graph. We cannot graph it, okay? We can't do it. This is the real plane. This is an imaginary number. Can't make it happen. So -2 does not exist as far as this graph is concerned, which means we have a limited domain. We have only certain x's that are going to work. So now we'll plug in our -1, so we'll have square root of -1. Again, I'm hoping, right, we're plugging it right into this function that you're like, negative under a root sign. This one is the definition of I. Can we graph an imaginary number on a real plane? No. Now we'll do square root of 0. So is there some number times itself that equals 0? And hopefully you're saying yes, it's 0. Square root of 1. So some number times itself is 1. It's 1. Now square root of 2, if I plug that right into our parent function right here, is not a nice number, okay? I would have to grab my calculator. It's actually an irrational number, which means that it is non-repeating and non-terminating. So calculator's up. I'm going to turn it, for me, I'm using my phone, so I'm going to turn it sideways, do square root, clear it out. I'm going to type in 2 and then the square root button. And I get 1.41, so we'll round that to 1.4. And it's one like hot mess after it, okay? It's a lot going on. The next one is square root of 3, and there's no nice number I can think of that square root, so I'll use my calculator again. I get approximately 1.7, that is rounded to the 10th place. Next, I have square root of 4, and that's nice. What number times itself is 4? Well, that's 2. And then, hopefully right now you're understanding why I chose 9, right? If we plug 9 in, the square root of 9 is 3. What would be another value here that would work well, that I wouldn't have to use my calculator for? 16, because that's the next perfect square, right? The square root of 16 is 4. And then the next one that would work out nice would have to be all the way up to 25, because the square root of 25 is 5. So it works best when I plugged in perfect squares, right? All of these worked out great. 0 is the smallest perfect square, 1 is the next smallest, 4 is the next smallest, then 9, 16, 25. So we'll graph even those gnarly decimals real quick. So I'm going to go over 2 up 1.4. We'll go over 3 up 1.7. We'll go over 4 up to the 2 finally. We'll go over 9 up to 3. And then we'd go way out to 16 and up to 4. And then we'd have to go even further for the 25. Okay? So you can see that this is clearly nonlinear, okay? And it starts increasing quickly, and then it kind of flattens out slowly over time. It's still increasing, just very, very slowly, okay? So when we create and graph these, we're going to keep in mind that the easiest ones to do are when we have a perfect square under the root sign, okay? And you're going to be required to do at least 3 points for every graph that you do, because if not, it could appear like a line, okay? 3 points is going to give us the trend of that overall curve. So we're going to be thinking we want under the root to be 0, under the root to be 1, and under the root to be 4, so we can try to use mental math. And that's going to bring us to our general trend on how we go about graphing ones that are a little bit more complicated, okay? So the first thing you're going to do every time is you're going to figure out which 3 x values you want to use in your table, okay? You are not just going to randomly put x's here. You need to know where it is that this graph starts, right? And that graph always is going to start where the inside of our root is equivalent to 0. And the inside of our root has a name. It's called a radicand. So when the radicand equals 0, that's going to be the starting point of our graph. Whether it's shifted up or down or to the left or to the right, it's always going to be where there's a 0 inside. So we're going to use that idea to help us figure out which x values go here, okay? So to figure out our x's, we're going to take our radicand and we're going to set it equal to, okay, so our radicand is just x plus 2. I'm going to set it equal to my 3 smallest perfect squares. The first one being 0. The next one being, if we look over here, right, the next easiest was when the inside equaled 1. So I'm not going to use, I'm not going to use 1 for my graph here. I'm going to say my inside has to equal 1. And the next easiest is going to be if my inside equals 4, because I can square root it in my head. So when my inside, or my radicand, equals 4. Now I'm just going to go about solving them. So I'm going to minus 2 minus 2. I get x equals 0 minus 2, or x is going to equal negative 2. That's going to be the first point that I'm going to be able to plot on my graph. Next, I'm going to minus 2 here, minus 2 here. X is now alone. 1 minus 2 is negative 1. And then the final one, I'm going to minus 2 minus 2. And I end up with x equals 4 minus 2, which is 2. These are the 3 x values I have to do. You have to do this step first, okay? Figure out your x's. Then it's pretty easy. You're just going to take each of those x's, plug them into our original equation, and get out the other half of your coordinate pair. So I'll write this one out. Instead of having x plus 2 on the inside, I'm going to have negative 2 plus 2 on the inside as my radicand, and then a plus 5 on the outside. Well, the square root of negative 2 plus 2 is the same thing as the square root of 0, and the square root of 0 is the same thing as 0. And 0 plus 5 gives me my answer for my y. My answer for my y is going to be 5. So I'm going to go over negative 2, up 1, 2, 3, 4, 5. That is the first point, okay, remember, because it was a 0 underneath the root, that's going to be the first point where things exist. If I were to plug in, for example, negative 3 here, negative 3 plus 2 is going to give me negative 1. I can't plot that. It's imaginary. This is the lowest number we're going to be able to get, okay? And that will always happen if you set it, your radicand equal to 0, your radicand equal to 1, and your radicand equal to 4. You will always get this as your starting point, okay, whichever one was corresponding to the 0. Let's take a look at negative 1. So we'd plug in a negative 1 here. So we have square root of negative 1 plus 2, and then a plus 5 on the outside. Well, negative 1 plus 2 is 1, so I have square root of 1, which is 1, plus 5 is 6. So I'm going to go over negative 1 up 6. And then my last one is a 2 here, so I'll put a 2 right there. Okay, 2 plus 2 is 4, so I technically have square root of 4 plus 5. Well, the square root of 4 is 2, so I end up with 2 plus 5, which is 7. So my coordinate pair is over 2, up 7. Now again, my graph is always going to start wherever this 0 was, okay? So it's going to go boom in this direction. If you're not sure where it starts, it's always going to start with whichever one was equal to 0 when you simplified inside your radicand, okay? And there's your graph. Done. Perfect. Beautiful. Love it. Okay? Let's come to another graph. And each of these are going to be a little different, right? This one, technically, it usually starts at 0, 0. It moved up 5, and it moved to the left 2, which is a translation here and here. Now, this one is going to have some translations also, and maybe they feel familiar to you, but when I taught this to my honors class, they said they don't use that strategy as much. They prefer to do it as a table, which is why I'm teaching it to you this way this year. So this would be a shift up. This is going to change the magnitude or the steepness, and then this is going to be a reflection. So it's either going to look upside down or backwards. So we're going to do our 2 steps. In our first step, we're going to take our radicand, just the 2x, and we're going to set it equal to 0. We're going to take our radicand, we're going to set it equal to our next lowest perfect square, which is 1. And then we're going to take it one final time and set it equal to 4. Now this one's a little different in that we're not adding something or subtracting it, we're dividing. So we're going to divide by 2, divide by 2. We end up with x equals 0 divided by 2, or just x equals 0, right? 0 cut in half is just 0. Next, we're going to divide 2, divide 2. This one does not turn out nice. Just because you get a fraction doesn't mean anything, okay? I know it's going to feel complicated, but it's going to work out nicely in the end, okay? So I'm going to use x equals 1/2 as my next one. And then my last one here, I'm going to divide 2 on each side, and 4 divided by 2 is going to give me a nice number. X equals 2 for my last one I'm going to do. So now that I have my 3 x's, all I need to do is finish the other half by plugging them in. So right now, I'm going to plug that in here, okay? So it's not 20, right? It's 2 times 0, which is 0. So I technically have negative square root of 0 plus 2. The square root of 0 is 0. Negative 0 plus 2 I know seems silly, but that's just 2. Okay, so my first point is going to be over 0 up 2. The next point is where I think you might feel like it's going to be a little bit trickier, okay? So let's just erase that off. I'm going to plug in a 1/2 right here. So we have 2 times 1/2. Now a whole number times a fraction, we put it over 1. We go across the top and across the bottom. You hated this 1/2 right now, but look at this. 2 times 1 is 2. 1 times 2 is 2. 2 over 2 is just 1. So you technically have negative square root of 1 plus 2. Well, the square root of 1 is 1, so negative 1 plus 2. And negative 1 plus 2 is just a positive 1. So I'm going to go over half a box, and I'm going to go up only 1. Now, you might be confused right now, like, shouldn't this be up here? All of our graphs have looked like this so far, right? Well, remember, I had mentioned that this negative is going to make it a reflection. This is going to make it look upside down because we're multiplying by a negative outside of our root sign. Last one, I have this 2. I'm going to plug in a 2 right over up here. So I'm going to have 2 times 2, which gives me 4. So I'll have negative square root of 4 plus 2. Well, the square root of 4 is 2, so we have negative 2 plus 2, which is just 0. So I'm going to go over 2, up 0, over 2, up 0. And starting with wherever this happened, right, this coordinate pair is where it starts. And it's going to go down like that. Okay, so again, this was a reflection upside down, and it actually is a little bit steeper than it normally would be. Here it kind of flattens out quicker. Here it went down 1 box over a half. Here it went 1 and 1. Okay, so that is a little bit steeper. Let's do our third one, okay? So this was like easy, this was like medium, this is like as hard as they're going to be getting for you, okay? And we want to practice one of each, right? Because that's how we get better at math. This will also be the last example that we do together, and then you folks are welcome to give a go to your homework. So our first step is to find our 3 x values from our table. Okay? We're going to take our radicand only, x plus 12, and we're going to set it equal to 0. We're going to take our radicand and we're going to set it equal to 1. And we're going to take our radicand and we're going to set it equal to 4. And again, the reason why we do 0, 1, and 4 is because those are the 3 smallest perfect squares. So now we're going to get those x's alone and positive, and that'll be the x values that we're going to use in our table. So I'm going to minus 12 minus 12. That gives me negative 12. I'm going to go a little quicker here. I'm going to minus 12 minus 12. That's going to give me a negative 11. And in my last one, I'm going to minus 12 minus 12. That will give me a negative 8. Okay? So now this is where the real work's going to start happening, okay? This is a long equation. When I plug things in here, this is going to simplify nicely, but you know I have a coefficient I'm multiplying by here. That's a fraction. Okay, so that's going to change some stuff. So I'm going to plug in a negative 12 here. Negative 12 plus 12 is 0. I knew it would cancel to 0, right? I made it that way. And the square root of 0 is 0. So I currently have 3/4 times the square root of 0, which is 0. And then a plus 3. Well, 3/4 times 0 cancels. I'm left with only 3. So I'm going to go negative 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and I'm going to go up 3 and put my first dot. That's where my graph is starting. Hopefully it's going forwards and not backwards. Now let's do our next one. Okay, I'm going to plug in negative 11 here. Negative 11 plus 12 gives me positive 1, so I currently have 3/4 times the square root of 1 plus 3. The square root of 1 is just 1. So 3/4 times 1 is 3/4 plus 3. I don't care if you keep it as a mixed number, folks. It's 3 3/4. That's easy. You're graphing it, right? You want to know where it is. So I'm going to go negative 11. I'm going to go up 3 and then 3/4 of a box. Boom, right about there. So our last one here we have is negative 8, and that one we'll just plug it on in and keep going with it. So I'll put a negative 8 here. Negative 8 plus 12 is positive 4. Again, I knew I was going to get positive 4 because that's what I meant to happen, okay? So our coefficient is still 3/4 times the square root of 4 plus 3. Well, the square root of 4 is 2, okay? And 3/4 times 2, I need to put that 2 over 1. So I end up with 6 over 4. 6 over 4 is the same thing as 3 over 2. So I currently have 3 halves, right? 3 times 2 is 6. 4 times 1 is 4. Each can be cut in half. Now, if you know anything about improper fractions, hopefully this is recognizable to you as 1 1/2. Okay, so I can just rewrite that as a mixed number, 1 1/2. So 3 plus 1 1/2 is going to give me 4 1/2. I don't know why I put a decimal in the 1/2. It should just be 0.5 or just the 1/2. Sorry about that. So I'm going to go over to -8, which is here. I'm going to go up 4 1/2 of a box. Okay. But, ooh, that was bad. But you can imagine it went through the point that it should have, right? That's a little bit better, but not much. This is the process I want you to go through when you're graphing square roots. You're going to take your radicand, okay? Just the radicand. And you're going to set it equal to 0, equal to 1, and equal to 4. Because those are the 3 smallest perfect squares. It's going to make it so that finding your y values, finding your outputs are going to be easier, okay? So that will give you your 3 x's. Once you have them, you're just going to plug in those 3 points. It will always give you the starter and the following 2 that you need to define the curve. Your homework is to do this 6 more times, okay? I wanted to provide you with lots of practice. I don't want to keep talking at you. I want you to give it a go. I am, and already have, created the key for this homework. It is not going to be posted on today's lesson. I will post it for future lessons. Feel free to make your table here and maybe do your x values here. I tried to leave you some work for each. If you are struggling, then feel free to attend office hours, and I can show you the key right then so that you can see if you were doing it correctly or incorrectly, okay? Please take some time and really think through making these 6 graphs, okay? Each one, the easier ones will each be worth 1 point, and then the harder ones will be worth 2 points apiece. Okay? Thank you, folks. I look forward to seeing you during office hours if you have questions. Otherwise, I hope things are going well. Talk to you later. Bye.